All right, so welcome back. Now we're going to look at three groups of preschoolers and their language score. Group 1 spends 5 hours per week in preschool. Group 2 spends 10 hours per week in preschool. And Group 3 spends 20 hours a week in group preschool. So this is what it looks like. These are their language scores based on what group they're in. So first, we're going to state our null and research hypothesis. So in this particular situation, there's going to be no difference in the language scores based on the time spent in a language immersion preschool. Whereas the research hypothesis, which is not the hypothesis we test, but it's the one that we really want to have be true, there will be a difference in language scores based on the amount of time spent in a language immersion preschool. We're going to set our level of risk to 0.5, which is where we always start. And because we're looking at language across three groups, right? So language scores are a dependent variable, and then the number of hours spent in preschool is going to be our independent variable across three groups. We'll choose a simple ANOVA. Now, we're going to calculate the F ratio for this one. And we're going to look at the between group and within group sum of squares and our total sum of squares to calculate those differences. So let's do this by hand. All right. So I would encourage you to pause your video and try to work this out and see if you come up with the same solution that I do. All right. And to help you get started, you're going to fill in this chart. Okay, as much as you can. And then you're going to use that to calculate these formulas, come up with an answer, and then divide this. All right, so I will now go through that. So if you wanted to do it, make sure you pause the video and do it. It is a good practice to try to do it. Okay, so first things, I have all of my test scores for group 1. So this is group 1's test score. I'm going to take each one of these scores and I am going to there we go. I'm going to square that. So 87 squared equals this. And then I'm going to do the same here. I'm going to total up the total number of people that were in group 1, and I'm going to come up with my sample for group 1. And then I'm going to total up the total scores, and I'm going to come up with my summation of group 1. So the subscript is the group number. So the summation of group scores is 766. I'm going to square each one of these scores, and then I'm going to sum these squares. And when I do that, I'm going to get this. Same thing for group 2. Going to add them up. Got 10 in the group. Going to sum up the independent scores to 852. Going to square each of my scores, and I'm going to sum those squares. I'm going to do the same thing for group 3. I'm going to square, and then I'm going to add up each one of these columns. All right. I love doing these in charts because when I do these in charts, it makes this whole next part much easier. So the sum of X for group 1 is right here. So I'm just going to bring that down. Okay. X bar, I'm going to calculate the mean for this, which I've done. All right. Which is the total number of scores divided by my n. So that's pretty easy to do. So I just add this up. So I'm basically taking this and dividing it by 10, and that gives me my mean. Now I'm going to take the summation of X squared, which is right here. And then I'm going to take the summation of X. So this is this number. This is the summation of X. All right. So the summation of X squared, which is different than this. So the summation of X is 766 squared. So I'm going to square that, and then I'm going to divide by n. And when I do that, I get this number. I'm going to repeat this for group 2 and 3. Now, this capital N here means it's the total of the groups, because this is my whole population, is these 3 samples. So when I do my total, that's going to be 30, right? 10 plus 10 plus 10. Now I'm going to take the summation of the summation of X, which is this row right here. So I'm going to sum up these. I'm going to add them up. Now I'm going to take the summation of X squared divided by the total number in the population. Now I'm going to take the summation of X squared. So this summation of X squared, so it'd be this. So I'm going to take each one of these and add them up. And then I'm going to take the summation of these three and divide by n, which I've already done. So I'm just going to add up those totals. Now I'm going to bring these down. So my between sum of squares is this one right here. Okay. So I'm going to take this one minus this one. So match them up. So summation x squared divided by n, which is this one right here. And I'm going to divide it by this one right here. And that is going to look something like this. And here I'm going to take the summation of x, this box right here, and I'm going to divide it by this number for my within sum of squares. See, it takes a lot to calculate an F statistic. And for my total sum, I'm going to take the summation of x squared divided by this one. So that's my total sum. And when I calculate these out, I get these scores. Okay. Now I'm going to take that formula and I'm going to divide my between here, this number, and I'm going to take it and divide it by the within. Okay. And so that's calculated over here. I'm going to bring those back down. Those are just these numbers right here. Bringing those down to help me. I need to calculate my degrees of freedom. K is always going to represent the number of groups. So the number of groups is 3, right? I had 3 groups of language. So that's 3 minus 1 equals 2. And so my between sum of squares is going to be this number divided by the degrees of freedom. And that is going to give me this number. My between sum of squares is divided by the degrees of freedom, gives me my between mean sum of squares. Here's my within sum of squares. Now it's n, which is 30, the all capital N, and then k, 3. So I'm going to subtract 30 minus 3 to get 27. I'm going to divide those out. And it's going to give me 64.3. And then total sum, which I'll need in a little bit, is going to be 2 plus 27 degrees of freedom for 29. So 2 plus 27. Now I'm going to divide this mean sum of squares, 566.49, and I'm going to divide it by my within 64.39. And that, when I calculate it up, is going to give me 8.808 when I round up. It's really 8.799. When I round up to 2, it's going to give me 8.80. Now I have to go to my statistical tables here to determine our critical value, because this is our obtained value. So we're going to go to our critical value. Now we've calculated our degrees of freedom already. Our between group is 2, which is our numerator, and our denominator is 27. So let's take a look at our statistical table that we've been using. We're going to go to the F distribution. So we're going to scroll down until we find the F distribution. And this is our numerator. So it's 2. And our denominator is down here. So that's 27, which gives us 3.35. And this is for the 5% significance level. If we wanted to do 1%, we would be able to go here to this one, right? And we'd still use the same degree of freedom, which in this case would give us a 5.49. Now, because this one was This was 3.35, and I know my obtained value is 8.80. I'm going to go ahead and check the 1%, right? Because it might be significant at the 1%. And sure enough, I come here, I go under 2 for my numerator, and I come across from my denominator to 27, and 5.49 is my cutoff here, my critical value. So I can say that this particular finding is significant at the 0.01 level, the 1% significance level. All right, so that's all explained here. I'm going to compare those. Like I said, 8.80 is definitely greater than 3.35. So I can say that it is significant. And here's where I explain why I went to the 1%. And I can actually say that it is significant at the p less than 0.01 level. So, interpretation, 3 groups of preschoolers demonstrated differences in language score. And here is my sentence of my data. Okay. So oftentimes students will say, oh my goodness, Dr. Elliott, that was a lot. So why do we not just run multiple t-tests? Well, whenever you run a combination of tests between like group 1 to group 2, group 2 to group 3, group 3 to group 1, all of that, you want to set your p-value at 0.05, right? Because you're only willing to accept 5% chance that chance alone is at play. Well, here's the problem. Every time you run a t-test on a combination of data, your T or type 1 error, your risk for type 1 error increases. 1 minus the significance raised to the K. So if I have, a certain number of comparisons, which is what the K represents here, I have to count those comparisons. So group 1 to group 2, group 2 to group 3, and group 1 to group 3 to truly understand the differences between these groups, which is going to give me 3 observations, which is equal to my K. Okay, so my K here is equal to the number of observations. So when I use this formula to determine the actual risk of comparing these individually as pairwise comparisons, it's going to actually raise my significance level to 14.26, which far exceeds the acceptable significance level of 5%, our alpha level. So our risk is going to be 14.26% that chance alone is at play and not what we're actually studying. So for that reason, we're going to make sure that we use an ANOVA and not multiple t-tests when we're looking at one group of data. All right. One other thing is the effect size for ANOVA is called an eta square, which looks like this little guy right here, an eta square, which is the between group sum of scores divided by the total sum. I told you we we're going to use this piece of data right here. Okay, so we got to take the between group sum of squares and we're going to divide it by the total sum of squares. And so when I do that, it's going to look like this. So this is my between group sum of squares divided by my total sum of squares. It's going to give me an eta square of 0.39. So according to this chart, that gives us a small, medium, large guideline, or according to the small, medium, large guidelines for eta square, 0.39 is a large effect size. Now let's do this in JASP. Okay, so let's take a look at JASP. So this data set is in your class file, your class data set. So this is JASP. You can see that the groups are set to nominal, which they should because that's our independent variable, the number of hours. And then our language scores are all listed here. Note when you're setting up an ANOVA data set, you break it out by group. So you assign each person to what group they're in, and then you give their score. So group and score. We're going to go to ANOVA, classic ANOVA. We're going to put language score in our dependent variable. We're going to put group in our fixed. Take a look at this. We have a significant source table, significant finding with the F score of 8.7991. That doesn't surprise us because we already know based on our manual work. So whenever you're asked to do manual work and JASP work, you can compare and see, are they right? Am I right in my manual work especially? Here's my numerator and my denominator. Okay, so my numerator and denominator. So this is my between group and this is my within group. Let's go back out and do a few extra things. We'll get some descriptives. We'll get our estimate of effect size. We have our model already. We're going to do our assumption checks of homogeneity test and our QQ residuals. We're going to go to post hoc because we know we have a significant finding. We're going to move group over here. And I'm just going to do Bonferroni. I can also display confidence intervals if I want. I can do descriptive plots. I can move my group to the horizontal and click my error bars at a 95%. Let's see. Nope, I don't think I need any of these. And I don't need non-parametric unless I violated my assumptions. So let's take a look. So here's some descriptives. We can see our mean, standard deviation. We can see our descriptive plots. I don't see any outliers. I can also see that there's some overlap between these, but there's no overlap between this one and this one. So that makes me think that I'm probably going to find there's a significant difference between 5 hours and 20, but not between 5 and 10 and 10 and 20 because they overlap. on the hour bars. Let's see if I'm right. Our assumption check, this p-value on the Levene's does exceed 0.05, which means we have normality. I can see for the most part, I can see there's linearity. There's some deviation here, but not enough to worry me. And then I'm going to look at my post hoc. So 5 to 10 hours is not significant. You see that, which was not surprising, right? So what was that? 5 to 10? Because they overlap here. See how this error bar overlaps? So that doesn't surprise me. 5 to 20 is significant. Okay, again, doesn't surprise me because I can see these guys don't overlap. The 5 and the 20 don't overlap. And then for 10 to 20, not significant. Okay, and again, the error bars showed that. So here's the explanation for everything that I did. We tested our assumptions, they were met. No outliers. We tested for the Levene's. We reported our results. Our Q is described here. Here's where we interpret all of our assumptions. I'm going to interpret the ANOVA, making sure I give an accurate table or chart here, or sentence here. Again, this is the template for writing your test statistic findings. My ANOVA has an effect size, so it is larger than 0.14, so it's a large effect. I report my results, always matching my data with my description. Because I have a significant finding in my source table, I'm going to also test for post hoc. And here I reported on both types of post hoc. There's other types, but these are the most common. Here's how I interpret that. I also did error bar graphs to graphically demonstrate my data, and I reported on all of that here and gave a description of the data that I had collected. And that is an example of a one-way ANOVA. I also wanted to show you this resource. So let me pull that up. So on the statology page, they actually have something similar to what we looked at when we looked at chi-square, where you can actually plug in the data for your groups and you can hit calculate, and it will calculate your between, subject, and error and give you the answers as well. It won't give you the test of the assumptions and things like that, but if you just want to run a quick analysis to see if there's differences, this might be a good starting point. So it's an extra tool. So that is the review of how to do a one-way ANOVA.